Yeah.
Yes. Okay. So, good afternoon, everyone. First of all, thank you so much for giving me here this opportunity to talk a little bit about the work I have been developing in the past years. I'd like to thank the Unite. I'd like to thank also Professor Luis Picado Santos, my colleague, also Eva and all the people that are part of the Unite, and also greet the students. So I saw that you all had amazing questions, and I hope that I can answer them during the presentation, but also during the discussion afterwards. Okay. So before going into the topic, just a brief description about myself. So since June 2025, I started a position here at Lisbon as a professor, as assistant professor. I did my PhD here at the University of Lisbon in the Técnico in transportation systems when I finished in December 2023, and also did part of my research at the Technical University of Denmark in 2022. So my nationality, I'm actually Brazilian. So I did my bachelor course in Brazil, the 5-year bachelor course in civil engineering at the Federal University of Rio Grande do Norte. But I also did part of my research at the University of Toronto, and where I stayed for a year and a half. Okay, so going into to just um minuto. Cara, não posso falar agora. So going into the research topic, so I'm going to talk today about allocating space dynamically over time. Okay. And the first message that I want to say to you is that when we think about allocating road space or urban space dynamically, this is not something new in practice. Okay. So just to show you some examples. So this was a photo that I took when I went to visit Lund in Sweden. And I saw this very interesting dynamic where you had children playing on the square. You had the skateboard where people would play in skateboards, right? And then a month later, I went there again, and the space was completely changed, right? And so now you have like food courts and people were using the space differently. And even if you look at the space, you see that even the audience change depending on how you use the space. So in the first picture, we had more children. Now we have a more adult public using the space. So in Lisbon, we also have some kind of examples of this, of allocating, let's say, space differently in different times of the day. So this is for people in Lisbon that are watching. This is Avenida Duque d'Ávila. That is the street that cuts the front of the university where we are. And every Thursdays and Fridays, this street becomes a market, a street market. So a place where people used to just move, right, from point A to point B. Now people stop, they socialize, they buy things at the shop, right? And so this is just to show you some very simple examples of if you change the way the street is planned, or you put urban furniture in the street, people will use the space differently. And of course, that when we think about allocating space dynamically, of course, that these are very simple examples. And they are very simple because of many reasons. They are simple because, first of all, you don't have a conflict here of many uses, right? So there is a lot of space, so you don't have a lot of conflict. The other thing is that when we have a market, well, this market is during the whole day, right? So it doesn't change in peak and non-peak hours, for example. That is way more complex. So these are very simple examples because of these reasons. But if we look at cities, and if we think about cities, how they are actually planned, this is not, there are a lot of streets that are very complex. And so if we think about how traditionally transportation infrastructure has been planned, so usually what has been done is you usually do traffic counts during peak hours, right? And you try to dimension the infrastructure to support that maximum capacity during peak hours. And this has a lot of problems, but one of the problems of this type of infrastructure is that, okay, during the peak hours, maybe this infrastructure is fulfilled its capacity, but during non-peak hours, this space is probably underused. And so there is this kind of inefficiency of the use of space if we think about how the space is used over time. Okay, and so the idea of this thematic of this also of this work is this idea that we can change the space according to the fluctuations of demand during the day or during seasons, etc. And so today, the objective of this talk is to try to evaluate current ways to reallocate space dynamically over time in more complex streets or complex urban areas. And so, a concept that is extremely important here to mention is this idea of complexity, right? And so when I mention complexity here, what I mean is streets that are limited in space, so there is not sufficient space, and there is a high dispute in uses in these streets. And so it's not that evident the amount of space that should be allocated for certain transportation mode or certain function in the street. And so today I'm going to talk about four main topics regarding reallocating space dynamically. The first one is, okay, based on what I want to propose, what are the differences of what already exists in the literature about reallocating space more responsively and what type of technologies also exist? The second question is, okay, how can we allocate space dynamically? What technologies can we use? Where and when does it make sense? And the last one is, how do people actually accept these type of solutions, right? The first three questions, they were mainly developed during my PhD. And this fourth question is a research that has been held by a master student that I have supervised together with Professor Felipe Moura and Professor Matheus Humberto. That is Matheus Humberto from the University of São Paulo. So going to the first question, what already exists in the literature about these more responsive allocation, dynamic allocation of space? Of course, the first step is to try to do a literature review, right? And so we did a systematic literature review based on the main journals of transportation and urban studies, but we try to incorporate two different things here. So we try to incorporate here text mining techniques to analyze first the historical context. So how do certain concepts of technology, for example, they emerge in the literature over time? And how does this influence these new, more responsive road space allocation? And then afterwards, analyzing the full papers, okay? And so going to the historical analysis, what we did was we analyzed, first of all, we did an algorithm using R programming to just count the most frequent words that happens in abstracts every 5 to 5 years. Okay. And so we tried to see what were the trends and how these trends went over time. So this is just an example of all the 5 and 5 years. I know it's very difficult to look. So we're going to focus on the three last periods. So if you look at 2006, 2010, and these are the words, more frequent words in the literature, you see that, for example, in 2006, 2010, and 2011, 2015, the word traffic is very relevant, right? And something that we noticed is that also the word smart began to appear in the literature as relevant from 2011 and beyond, okay? And so if we compare this to the 2016, 2020, something interesting that we notice is that the word traffic that was very relevant loses some importance to the word mobility, right? And the word smart, for example, that just appeared in the literature from 2011 to 2015 became one of the most important words in the literature from 2016 and beyond. And so this is just an initial analysis to see how different trends you have in certain topics or in certain over time based on historical analysis. And so from that, what we try to do is, okay, we're going to analyze now the full papers, okay? And so the papers that were really related to more responsive allocation of space. And one of the things that we notice is that, first of all, we try to get from this another analysis that is called topic modeling. And so it's a more complex analysis than just word frequency. So here what you do is a type of probability analysis of the words being together. So here we have 6 main topics in the literature, and we run it through the whole paper. And so just to show you topic number 1, to give you an example, you can take a look and you can see that there are words such as dynamic, road, space, allocation, but you also have words such as cost, time, traffic, car, bus. And so from this topic, you can already have a clue that allocating road space dynamically over time in the literature is very traffic performance oriented, right? It's very oriented to optimize generalized costs, the travel time, costs, and especially focused on the bus and the car. And so this is just to give a hint on the main topics that are in the literature. And so based on this methodology, one of the main concepts that we found is this concept of dynamic lane allocation. And the concept of dynamic lane allocation has many applications. So one of them is this idea that you have a traffic lane or a bus lane, and at the peak hour, it's a bus lane, but during the non-peak hour, this could be mixed with traffic or could be used for another purpose, right? The other example is this idea of reversible lanes. So these are traffic lanes that during the peak hour in the morning, let's say you go in one direction, and then during the peak hour during the afternoon, people are coming back home, and so the traffic lane goes in the opposite direction. And there is also a lot of literature talking also about this inclusion of autonomous vehicles, for example, and the allocation of space very responsive to the demand of autonomous vehicles. So if we look at the literature is actually very focused on, first of all, expressways and arterials, so highways, right? They're not very focused on urban areas. It's very traffic performance oriented. And this, in terms of expressways, makes some sense. But in urban areas, you need to consider other functions of the street, right? Also, in terms of the architecture of the models, they only consider the traffic lanes are considered, right? And so in more urban areas, you also have to consider the adjacent space of the street, such as the sidewalks or even parking spaces. And they are very focused on bus, automobile, rescue vehicles, and autonomous vehicles. But in urban areas, you also have to include vulnerable users such as pedestrians and cyclists and other types of users. And so the idea of this work is to actually expand this idea of allocating space dynamically, but to more urban areas, right? And to include and to check if this is appropriate or not, and where is this actually appropriate. And so to demonstrate this, what I would like to show you initially is this graph. And in simple terms, in terms of allocating space, what this graph shows is that depending on the hierarchy of the street, you have certain amount of space that is allocated for mobility, for circulation, or for access. And so if we have an arterial or an expressway, for example, you tend to have more space for circulation, so more traffic lanes, and you tend to have a minimal space for parking, right? Or for access to activities. In the opposite, in the local access street, you tend to have more space for access, so more space, let's say, for parking spaces or even for sidewalks, and less space for the traffic lanes. But before that, so if we look at the literature is very focused on this left side of these curves, right? Very focused on highways and dynamic lane allocation. And so the idea here is to actually try to focus here on these complex areas. And so if we look at some streets, it is not that evident the amount of space that you should allocate for access function or for the mobility function, right? Some streets have a high dispute in uses. They have a high dispute in activities, in land uses, as I will explain. And so it's not that evident the amount of space that should be allocated for one mode or the other. And so the idea here is that we believe is that allocating space dynamically could be a solution in some cases when you consider also this temporal dimension of how the space is actually used over time. So going into now, how can we actually allocate space dynamically? Let me just give you some examples. So let's say you have a street And in the street, during peak hours, you want to give preference to the bus. So you could use some LEDs, let's say, in the street. The red LEDs could inform the drivers of the motorized vehicles not to enter the bus lane. And then during non-peak hours, when the frequency of the buses, let's say, reduces, and also the volume of cars reduces, maybe this lane can be mixed with traffic, or this is just, of course, an example. The other example is that you could have a parking space. And this parking space, let's say during the day, people go to the office, right? And they are in the, you use the parking space. But during that night, when people come back home and this area becomes more susceptible to bars and restaurants, maybe these areas are underused by car parking and could be used for more other uses such as restaurants and bars. And you could use simple technologies such as flexible borders to ensure the safety between the vehicles and the pedestrian. But of course, these are just these are of course just examples. Okay. So there are many technologies that could be used to allocate space dynamically. Let's say such as flexible borders that could go up and down, could indicate these uses. You have variable meta signs. These are technologies that could inform the many uses that you could change over time. So you could say that at certain hour the space would be used differently. LED pavement lightning that could change the color, for example. So these are technologies that are already used in practice, right? But of course, that you have also some other types of technologies that are being developed, more demand responsive. So you have the technology of dynamic streets, for example. That is a modular pavement that was created at MIT from Professor Carlo Hatti and his team. And so these are modular pavements like hexagonals. And so you can change the lights. So this can change the function of a street. You can install bollards. You can adapt the space. And you also have one that is even more responsive. There is this idea of stalling crossing. So the stalling crossing is a LED pavement. When the pedestrians, they arrive to cross the street, a crosswalk appears and also informs the driver to stop. So even if pedestrians, they cross the street informally, outside of this area, it also informs the driver that a pedestrian is crossing. So of course that this is a very high-tech and high-level technological prototype, but just to show you that some technologies are already being developed also in this direction. So we talked about the concepts, right? The different concepts, but something that we wanted to analyze also is, okay, we know that there are concepts of reallocating space more responsively, but we want to know what type of technologies could be used to allocate space dynamically. And so we did another systematic review of the literature, focusing on technology and adopted these technological levels that we call, that goes from no technology, so just using a vertical sign, to a level that is number 5. There is this idea of futuristic scenario where you have autonomous vehicles and you have everything connected in a smart city, let's say, environment. And something that we notice is that when we think about allocating space dynamically, it can range from different levels of technology. And so it's not really dependent on technology, but could use it. And the higher the level you go, the more technological dependent you are, right? And so if we look at the practice, the common practice is very much in these lower levels of technologies, of not using technology at all, or using technologies that are not connected with each other. So you're not sensing the vehicles, the demand, and also adapting the infrastructure. So there are some examples in practice, especially in pilot projects, that you can connect the infrastructure, for example, to adapt for bus lanes, connected with let's say, with GPS in the vehicles, and so it could adapt according to the position. But this is not just some few examples. And there are some futuristic scenarios also with autonomous vehicles when you have the communication between vehicles and also infrastructure. And something very interesting that we notice is that if we look at the practice of what has actually been done in practice, the tendency is to go to lower levels of technology. But if we look at the literature, the literature is actually going the other way around, right? And so this is also a criticism a little bit to academia that sometimes thinks so much about the future, right? And does not really evaluate also the state of practice. And so this is also, I think, a contribution of this work that also focuses on more low levels of technology adoption to allocate space dynamic. So, of course, that's all of these ideas, so such as using real-time crosswalks, green wave for cyclists, like adapting the space with for non-peak hour use of street space for esplanades, for example, dynamic curbs that could change, as you can see here, the use during different times of the day. And of course, that all of these ideas, they are very pretty, they're very nice. But of course, they face a lot of challenges, right? They have a lot of challenges. They have a lot of barriers. They cannot be done everywhere. They could have some implications in terms of equity, for example, of acceptability, or even infringements in terms of built environment, right? Some built environments are not appropriate for these types of of allocation of space. And so what we wanted to try to answer now is, okay, where and when does this actually make sense, right? Does actually allocating space dynamically in complex areas or urban areas has a point and can solve problems in cities. And so to do that, what we did was, first of all, we tried to analyze macroscopically what is based on this idea of complexity, that are streets or spaces that are very complex to reallocate space, so that are limited in space and have a lot of disputing uses. So we try to use a macroscopic approach first to identify which zones are more likely to be complex to reallocate space, right? And this could have the potential to reallocate space dynamically. And so to do that, what we did was we first established a grid map. We took a case study of Lisbon. We incorporated a lot of data. So we use land use commercial census data. We use population census data. We also use general transit fleet specification data, that this is data for public transport. So we had the frequency of the buses over time in different times of the day, the schedule frequencies. But we also had the traffic levels in different times of the day using Google Maps API in the street in the network of Lisbon. And we also use OpenStreetMaps to see the morphology of the street and also to evaluate that. And so going back to this idea of complexity, so what is a complex street? What characterizes a street to be complex, to reallocate space, to have limited space, and to have a lot of dispute? And so what we thought is that there are a lot of conceptual assumptions here that imply that. So the first of all is mobility versus access dilemma. So it's this idea that some streets face this dilemma that, as I showed you, that it's not that evident the amount of space. The other element is connectivity. So if you have a street that is very connected to other places in the city, this will tend to attract trips to that zone, right? And so you should somehow, and so this will implicate in more complexity also in that area. In terms of land uses, we also try to identify spaces that were very dense. So if you have a place that has low density, then maybe in this area you don't have a lot of problems also, right? And so we wanted to identify areas that were very dense, that had this complexity. And another point that is extremely important is diversity of land use. And this is one of the fundamental elements to allocate space dynamically. Because let's imagine that you have an area in the street that is strictly residential. If the street is strictly residential, what will happen is that you tend to have two peaks of demand, right? People going to work in the morning and people coming back from work in the afternoon, right? But if you have a diversity of land use, what will happen is that you will tend to have different opening and closing hours of bars, restaurants, activities, of offices. And so this will have many fluctuations of demand and many needs that the street has in different times of the day. And so this is what also enables this idea of allocating space dynamically. And the other element that we considered as complex is to have high levels of traffic, right? If you have at least 1 hour of the day that you have very high levels of traffic, this also creates this dispute in the street. And so what we consider as complex is actually the intersection of all of these elements in an urban area. But let's say that you have everything, but in this street, you do not operate public transport. There's no public transport operating. So this does not mean that the street is not complex. What it means is that if you do have public transport, then the street will become even more complex. And so, because then if you have high levels of public transport and high levels of motorized traffic, then you will have also a dispute in space in the traffic lanes between these two elements. So based on these conceptual assumptions, we created some indicators to measure this quantitatively. I'm not going to go into many details on this, but we calculate the public transport frequency, the level of services, use some centrality measures, and also calculated the population ratio and entropy index for the diversity of land use. And so the idea here was, okay, we chose some indicators, we chose some requirements for these indicators, we did some sensitivity analysis, and then what we identified as complex and very complex zones are actually the intersection of all of these indicators established in the map based on the requirements that we established. And so based on that, what we consider as complex and very complex zones is this intersection. So in Lisbon, we found 20 zones based on this algorithm. And of course, this is only a screening of the territory, right? So we're identifying zones that could potentially have dynamically, could allocate space dynamically. But this does not go into detail on which street, for example, it's more appropriate to reallocate space dynamically, or which type of solution is also more appropriate. And so in order to move from a more macro analysis to a more micro analysis, what we need to do is actually take a look into the zones, right? And so going into these zones, what we did was we went to a second step that was inviting experts to do a workshop that I will explain now. So these are just some photos of the workshop. So it was held during COVID in the phase that it was already allowed to have these type of meetings. So we invited experts from academia, from public transport authorities, from the municipality, to also here help us in this idea to help this workshop. So what was the objective of the workshop? So first of all, the first task was actually to just make people familiar with the topic, right? And so we divided people in groups and we asked them to think about solutions or technology that could be used to allocate space, to talk within each other, within the group, and then present that to the other groups, in the workshop. And then the second task, that is the most important task, is, okay, based on the zones that we identified, the 20 zones that are complex, now let's look at the streets. So for each zone, we created this cause that, as you can see in the right part of the picture, that this is in zone 3, that is one of the zones that was identified. You have the street that has 2 photos of the street, right, and identifies the zones. And so here, the groups, they had to choose for different types of dynamic road space solutions, which type of street was more appropriate for them to implement these solutions. And so just to give you an example, one of the zones that was considered as complex was this zone 8 that we identified, okay? And in this zone of 200 meters, you have 5 streets that intersect this zone. And so the green group got this zone. So there was a group that got this zone to allocate, to examine. And what they identified is that to allocate space dynamically for a bus in different periods of the day, Rua Moraes Soares was the most appropriate, right? To allocate space dynamically for a cycle lane, let's say you have a traffic lane, and this could become a cycle lane in certain hours or during weekends, for example. Rua Moraes Soares was also the street Moraes Soares is also the most appropriate. And then to allocate the parking space to restaurants in different times of the day, they chose a different street that was Rua Jacinto Nunes. And so one of the conclusions that we took is that depending on the solution, different streets could be appropriate for different solutions. And so they had to do this for the many groups. We had 4 groups. Each one had to do this for four zones. And then on the last task, what we asked them is, okay, you thought about which streets are more appropriate, but now think about which criteria did you take to choose these streets for different solutions. And so one thing that we saw is that depending on the solution, they had to rank the criteria. And depending on the solution, the criteria was also different, right? And so this is something that is very important because it demonstrates also that the levels of complexity of different solutions vary depending on the space and depending also of the solution per se. So this workshop was actually very interesting because we also identified through the experts this idea of when does it make sense to allocate space dynamically. So let's say you have a complex street. This is an example of Avenida Almirante Reis. There is a street that has a lot of complexity, that has all of these elements of complexity that I identified, that I talked about. So let's say that you have the demands over the time, right? So you have the demand of cars over time. You have the demand of buses. This is just an example, okay? And you have the demands of cyclists and scooters. So there will be moments of the day that these demands is what we call conflicting demands. And so these demands, they are all high, independently of the mode. And so to allocate space dynamically during these times is very politically challenging because you would need to somehow take out the space for the car eventually that has a high demand and to give it to another mode. And so you could do that, but it for sure is the most politically challenged moment to reallocate space dynamically. But there are also moments of the day that the demands, the fluctuations of demand, they are complementary. And so what this means is that you have a demand of a certain mode that is way higher than the demand for the other, right? And so in this example, you have the demand of the bus that's way higher from the car. So it's maybe more justifiable to have a bus lane here dedicated during these times and give space from the car to the bus. So this is, of course, in more complex areas. But if you have an area that is only residential, for example, you don't really have a lot of complexity. You don't have a lot of, maybe you don't have density, but even if you do have density, you don't have diversity, and you don't have a lot of complexity of uses. And so in these types of streets, it does not really make sense to allocate space dynamically. And here the focus should be actually making spaces more livable and spaces more safe for children. So other types of tactical urbanism, for example, street experiments, other type of interventions here could be more appropriate than allocating space dynamically for different uses. And so one thing that we identified is that, of course, that this is very context oriented, right? And so there is this level, there is a high level of complexity. And one thing important is that allocating space dynamically could be used to identify conflicts, after identify conflicts, to be a very problem-oriented approach, right? What do I mean by that? So let's say that you identify in a street that trucks for delivery, they are parking during lunchtime in the second lane of traffic, right? But only during lunchtime they are doing that. And so maybe you could reallocate space dynamically to solve that problem specifically of the trucks during that time, right? So there is a higher complexity, of course, if you change the urban function. So if you maintain just the function of movement, so a bus and a traffic lane and traffic, it's the same urban function. But if you get a traffic lane and put there a market during a peak hour, non-peak hour, of course that this raises very high the complexity of the use of allocating space dynamically, and not necessarily is appropriate to do that. And some periods are more complex than others. So working hours, If you look at weekends, there's a lot of, in practice, a lot of things being done during the weekends that you have less demand. And so doing like open streets and stuff like that. The frequency and number of changes could also increase complexity. So you should also try to here to be parsimonious. So not try to change so much the space because people could be confused and also could have some problems of safety and even problems of acceptability and the use of technology. And so the use of technology, this is very important. There is still a lot to be held in terms of studies in this direction, especially how would people actually adapt or actually use uh, higher levels of technology in public space, especially different if we consider equity. So if we consider also the elderly or people with disabilities, how would these people adapt to these spaces that are dynamic also? And one important point is also this idea that the geometry of the street could also um, imply that maybe allocating space dynamically is not that current. So if you have a street that you want to put a dynamic bus lane, but this tree changes so much in geometry and even in functions during the segment. So let's say it starts with 3 lanes and then after 2 blocks it goes to 2 lanes and then goes to 4 lanes and then turns back to 2 lanes. Maybe it's not that's appropriate to to reallocate space dynamically. And so different solutions will differ in different levels of complexity. And so this is extremely important. And this is extremely context-oriented planning. And so now we discovered a little bit about where and when. And what we wanted to evaluate afterwards is, okay, how could people actually accept these solutions of reallocating space dynamically? And so, as I mentioned, this was a work that was led by Breno Boiani, that was a master student that defended already, that was supervised by me, Professor Felipe Moura, and also Professor Matheus Humberto, that is from the University of São Paulo. So when we were thinking about how to evaluate acceptability and how could people evaluate the solutions, um, we took a lot of time to think about how would we do that. And so this because one of the main methods that you use to evaluate acceptability of future scenarios is this declared preference surveys, right? Is this idea that you create a scenario, you show to people that scenario, and they will accept the scenario based on certain elements that could change. But the problem with that is that, first of all, there are few practical examples of allocating space dynamically. And so if people may answer a future scenario, but it will not represent the actual behavior if these scenarios would actually happen, right? And there is a difficulty also representing this idea of complex scenarios also in these types of methods. And based on the conclusion that we also took from the workshop, so allocating space dynamically, because it's very context oriented, and because it depends of the type of solution, the technology level that you use, the temporal complexity, how much changes do you make in space. So this would increase the complexity of using these types of methods to evaluate actually the solutions of reallocation of space. And so based on this reflection, this is just to show you how research works, right? It's always back and forward. So instead of focusing on the solutions, what we wanted to focus, we took a step back, and so we tried to focus on the problems. And we tried to focus on how people actually have these problems on the streets, and how people perceive barriers of the problems that they face in the daily basis at different times of the day. And if these problems they are different depending on the time of the day. So, for example, if they have a problem to walk and it only happens during lunchtime, maybe allocating space dynamically could be a solution to solve that problem at a certain period of the day. But if the problem is constant over time, then allocating space just statically without reallocating space dynamically could also be a solution. And there are problems that don't even involve allocation of space. It involves elements of maintenance or elements of enforcement. And so what we did was we rearranged the research question to check if and focusing on pedestrians. We could have focused in other types of users, but focusing what are the barriers that people face to walk in different times of the day, and if these barriers they change in perception after in different times at different times. And so based on the site selection that we had, we chose a complex street. So we chose Rua Moraes Soares. So this is, as you can see in the figure, it's a very chaotic street. Okay, you have a lot of dispute, you have a lot of commerce, a lot of residences. We wanted to focus on these type of environments that could have more problems for people to walk. And so what we did was we did a field survey. Okay, we did a survey obtaining responses from 8 a.m. to 8 p.m. And we asked people we had 29 statements of barriers of walking. And we asked people if they agreed or disagreed with these barriers to walk, right? And if they had those barriers at the time they were interviewed. Okay, so this is extremely important. So then we could actually analyze the difference between the periods of the day. And so for the sampling, we use the Lisbon gender and age distribution. We also use a minimum of 100 responses per period. This is based on the modeling that we would do afterwards that I'm going to explain. And so we created these statements, 29 statements, based on the 7 C's. That is the dimensions of walkability, and people had to agree or disagree. Okay, so just to give you some examples, we had this, for example. I don't feel motivated to walk because there are so many obstacles on the sidewalk. So people could agree or disagree to that, right? I don't feel safe walking because I'm afraid of being mugged or robbed. Or you could even have, I don't feel safe walking because there are so many vehicles on the road. And so people had to agree and disagree on that. So with this field survey, we actually had a very good sample. So we had 1,031 responses only on the street of Moraes Soares. So this is extremely important. We had 40% during the peak hour, 40% during the off-peak hour, and approximately 90% during the lunchtime. We had gender distribution that was also appropriate according to the census, and also the age distribution also. And so to actually analyze these statements, we use a model called the Rush model. And what the Rush model does, it detects the ability, it detects that people that answer the question, they have different levels of ability, and the barriers also, they have different levels of difficulty. So the main assumption here that we're making is that barriers to walk, they have different levels also to overcome these barriers. And so it's actually a very simple model. So if a person has an ability level that is higher than the barrier, then they will easily face it. If the person has an ability level lower than the barrier, then probably it's more likely that it will not overcome that barrier. Okay, so just to show you an example, let's say that we have 5 barriers and we have 5 people that responded. And so if you have person number 1, okay, that says that can overcome all the barriers, all the 5 barriers, he will have a maximum ability, right? If you go to the opposite, that is a person number 5 that only can overcome item 5, then it will have an ability of 0.2. Going to the barriers is the same logic. So if you have a barrier that only one person can overcome, then it will be the most difficult barrier. But if you go to a barrier that everyone can overcome, then this one will be the most easy barrier to overcome. Okay. And so what the Rush model does is that, let's say you have these, it says that these have a logistic distribution, and this is in the average ability of the user, you have here 3 abilities, 3 barriers: the yellow one, the red one, and the purple one. Okay, and so for the yellow one, the average ability of all the sample can overcome, that has a 50% chance to overcome barrier, the yellow barrier, and has a 20% chance to overcome the red one, and a 90% chance to overcome the purple one. Okay, so this is just to show you an example. And so after that, when we got all of the statements, we try to see how the items were difficult depending on the time. So one thing that we notice is that, first of all, although there could be changes during different times of the day, the most difficult barriers, the main ones, they are the most difficult barriers. And the most easy ones, they are the most easy. So the streams, they do not change, even though they could change slightly depending on the time. But we also saw some very interesting aspects. So first of all, that some barriers, they are perceived the same. So for example, having vehicles stopped, parked on the lane, right, had the same order of importance independently of time. The other thing that we saw is that the most difficult barrier, this was very interesting actually, was the presence of litter on the streets. And so this street, for people that know it, is it's a very chaotic street, right? And so this is also a very nice result because it demonstrates that sometimes we are so focused on smart cities and putting technologies and sensing and autonomous vehicles. But sometimes just having maintenance in the street can actually increase the levels of satisfaction of people, right? Just cleaning the garbage is also could actually have an impact in the city. The other point is that, for example, the sidewalk condition was only put here as very relevant during the peak hour. And this is actually very interesting because the sidewalk condition does not change in different times of the day. It's the same, right? But the perception is worse during peak hours. And this may be because people during peak hours, they're going to work. So they need a sidewalk condition to be appropriate to walk, and they work faster and they go to work during that time. Another thing that was very interesting is this idea of pollution. So when we talked about pollution, the perception of pollution having on the street is worse during off-peak hours and lunchtime than during peak time. So objectively, maybe during the peak time you have more vehicles, so maybe the levels of pollution are higher. But the perception is worse during off-peak time and lunchtime, uh, probably because people are using the space differently, right? So during the peak hour, they're going to work, so let's say, they already have in mind that they can coexist with cars. But during the off-peak hour and lunchtime, maybe they are actually having lunch, or they are socializing, they're using the space differently. And so this could also change the perception, and this could be worse during the off-peak and the lunch. So this to show you that now based on that, on how people actually perceive the barriers different times, you can try to find solutions to that. That could be involved with allocating space dynamically or not. It could be another solution, okay? And so this is just to show you some very brief stats that we use for the model requirements. I'm not going to go in much detail on this. And all of the codes being used and all of the data is also on GitHub for reproducibility. And so in terms of conclusion, to conclude here, so the concept that I wanted to propose is more related to allocated space in complex urban areas, using not only the traffic lanes, but also considering the adjacent space, the mobility and access functions. Technology is not required for this proposal. They could be used technology, but not necessarily. So how can we allocate space dynamically? So sensing, transport demand management, control technology. It's very context oriented, but we have to be somehow parsimonious, right, in how we change and the frequency of changes and the number of transitions and solutions. So this idea of identifying complex and very complex areas, but different solutions have different levels of complexity and also local criteria, and could be in conflicting complementary demands, but this depends also on political will. And one thing that we notice is that in terms of how people perceive barriers, the time of the day that has an impact, even though some aspects do not change, but not necessarily the perception match the objective measure of that element. And so before I go to the questions, just to show you that many of this work that was developed, what we try to do is try to put it all open source. So this is and now that I'm supervising also students, I'm trying to make them also do these steps. So just for the first work of the systematic review, you can go here and you can download the data set that we use, for example. You can also download the code that was used in our programming. And we even, one thing that I did is also to reproduce the results in GitHub to show full reproducibility of the methods. Okay, so showing exactly the step-by-step, the guidelines, what was done, what were the criteria, the assumptions, and reproducing the results from the work that was presented. Okay, so I invite you all to take a look at the GitHub and see other codes that we are also doing. And thank you very much. I'm so sorry, maybe I took too much time, but thank you so much for your attention. I'm now very happy to answer any questions that you may have. Thank you.